To the ITC Colloquium this week. Thank you all for coming. And today we have Nir Mandelker visiting from, well, actually from California currently. But so Nir did his PhD in the Hebrew University of Jerusalem in 2016 with Abishai Deckel, and then was a postdoc at Yale, also jointly with the Heidelberg Institute of Theoretical Studies. And then a KITP fellow at UC Santa Barbara. Oh, did you get to go to Santa Barbara at all during 2020?
No,
that's
it was all remotely over Zoom. It was very sad.
Since 2021, he's been on the faculty at the Hebrew University for Jerusalem. And Nir is an expert on the accretion of gas onto galaxies, particularly through filamentary accretion and the circumgalactic medium and all sorts of stuff like that we're going to hear a lot about today. So please, Nir, take it away.
Thanks, Jake. And thanks, Jake and Vadim, for organizing this. I haven't been at CFA since the pre-COVID era, so it's nice to be back. I want to share with you today some various aspects of ongoing work by my group and my collaborators and myself studying how one feeds massive galaxies and massive halos at high redshift during cosmic noon from the cosmic web. And let me start with just kind of very large, high-level introduction. Certainly when most of us think of, what is the extragalactic universe looks like, I think these are the images that we all have in our minds. Certainly the public has in their mind, beautiful galaxies. This is an image from the Hubble deep field. Each galaxy here appears to be an island universe. Of course, all of these are at very different redshifts. Every individual dot here, a point here, is a separate galaxy. Seemingly, vast spaces in between them. They don't interact with each other at all. But then when we run our numerical simulations, our n-body simulations of how the universe looks like, we get this, a very intricate, interconnected web of structure connecting every object, every halo, every galaxy in the universe. This is known as the cosmic web. We'll come back to this quite a bit during the talk. And of course, these two images look incredibly different from each other. And the question is, how can we relate this picture to this picture? And the answer is through understanding what we call the intergalactic medium. And just to put this in a bit more context now of the formation of galaxies themselves, one talks about the cosmic baryon cycle. The baryon cycle is how these three large reservoirs of gas, the interstellar medium, which is all the gas inside a galactic disk itself, the circumgalactic medium, which is all the gas that's not in the disk, it's outside the galaxy, but it's still embedded inside the dark matter halo surrounding the galaxy, and the intergalactic medium, which is all the gas that's truly outside the galaxy itself. Outside the halo itself. All these three large reservoirs of gas are all very intimately connected by accretion of a gas from the intergalactic medium flowing through the circumgalactic medium onto the interstellar medium, supplying fuel for star formation. Those stars form, evolve, die, explode as supernovae. When they explode as supernovae, they send strong ejecta, or strong winds, from the interstellar medium back out into the circumgalactic medium. Some of that gas, which doesn't have a lot of kinetic energy, goes up and falls back down to the interstellar medium again. That's known sometimes as gas recycling. Some of the rest of the gas actually makes it all the way back out into the intergalactic medium. And therefore, you can see that these two large reservoirs of gas contain within them the fossil remnants of past generations of star formation. And really, in order to properly understand how galaxies form and evolve in a cosmological context, we must understand the dynamics of the IGM and the CGM as well, and how they all interconnect with the ISM and the star formation of the galaxies. And of course, it's worth remembering that the interstellar medium plus the stars of the galaxy account for less than 20% of the baryons in the universe. More than 80% of the baryons in the universe live in the CGM and the IGM. So indeed, if we want to be able to talk about what the universe is composed of, we must understand the structure of the CGM and the IGM as well. Now, most of what I'm going to be discussing today is going to be relevant for a period of the universe known as cosmic noons. I want to place cosmic noon into context here, and this slide will also help me set up kind of perhaps a somewhat controversial question, which we'll come back to kind of like midway through the talk, so I want to spend a moment on this. This is the very famous Maddow plot, showing on the y-axis the cosmic star formation rate density. So the star formation rate per unit co-moving volume is a function of redshift. And you can see a very well-defined peak at around a redshift of 2. The typical story that we use to understand this is that at high redshift, star formation grows in proportion to the stellar mass as the galaxy population grows when galaxies are on the so-called star-forming main sequence. At high redshift, the galaxy population is dominated by very massive halos above 10 to the 12 solar masses, where we expect quenching due to feedback from AGN and from a stable accretion shock at the halo-virial radius. And this peak, which is what is known as cosmic noon, the peak of galaxy formation, peak of star formation, occurs roughly when the typical halo mass in the universe is approximately 10 to the 11, 10 to the 12 solar masses. This mass is going to show up a few more times in the talk, so let's keep this 10 to the 12 solar mass halos in mind. So, okay, we want to talk about the cosmic web. That's the other crucial context from everything that I've been saying. Galaxies form within the cosmic web. Now, very, very broadly speaking, you could divide the halo population into roughly 2 types. You have your typical halos, or your low-mass halos, that are embedded inside individual large-scale filaments of the cosmic web. And you have your very massive halos, which lie at the nodes of the cosmic web. And while these halos are arguably see a roughly isotropic distribution of matter in their immediate vicinity, these halos certainly do not, and they are fed from a few discrete directions by a few fairly narrow and fairly dense cosmic web filaments. And this is actually a qualitative distinction between massive nodes and more typical halos. Showing the same kind of view, but now looking in a simulation that my colleagues and I ran a few years ago with the repo code. This is looking at the hydrogen column density at redshift 4 in a slice. It's slightly less than 1 proper megaparsec at the time, showing a cosmic sheet shown edge-on and face-on. In the face-on view of the cosmic sheet, you can see several dense coplanar filaments. And all these black circles represent individual dark matter halos. You can again see that your standard or your typical mass halos are aligned along individual filaments, whereas the very massive halos, the large circles, lie at the nodes of the cosmic web and are again fed by a few discrete dense filaments in a non-isotropic manner. This cosmic web is a dynamical structure. These cosmic filaments are not static. They themselves merge and evolve as the halos. I thought we had solved that problem. Okay. The cosmic web filaments themselves merge and evolve as the halos merge and evolve, and they always work to continue feeding the central disk galaxy that's here. I'm going to skip the movie. I am going to try and show you the next movie, which I am hoping will work. Apologies for the technical difficulties. Let's try this. So cosmic web filaments, they merge and they evolve, but to first order, and you can actually prove this analytically based on the theory of Gaussian random fields. I'm not going to go into it, but you always expect very massive nodes of the cosmic web to be fed by 3 or 4 streams, and simulations tend to indicate, and you can kind of understand this analytically as well, though I won't go into that. The 3 or 4 streams that feed an individual halo tend to be coplanar, at least within the vicinity of the halo. And that leads to some very interesting consequences. These streams, obviously go on to supply growing galaxy disks with mass. They're the main source of gas accretion onto the nodes of the cosmic web. But in addition to that, as I hope to show you in this movie, they supply disks with angular momentum. In this case, you can see 3 coplanar streams that are going to feed a growing disk galaxy and spin it up in a coherent way due to an impact parameter between the center of the galaxy and the axis of the inflowing stream. And in addition to that, the streams also drive turbulence and disk instabilities in the growing galactic disk itself. That'll actually be the topic that I'll be discussing in the lunch today, how to drive turbulence in galactic disks with streams. But let's see if this movie will play. So this is an evolution of a galaxy from redshift 6 to redshift 4 from the Vela cosmological simulation suite. this structure of in-spiraling streams through the circumgalactic medium toward the growing galactic disk at the center is at least qualitatively consistent with observations. These are KCWI observations by Chris Martin showing narrowband Lyman alpha emission and showing a velocity pattern which shows large shear over 100 kiloparsec scales, which has been shown to at least be consistent with the structure of kind of in-spiraling cold streams carrying angular momentum down toward the galactic disk. Staying in the realm of observations for a moment, what observational evidence do we have for these cold streams or cosmic web filaments or them being responsible for feeding galaxies at high redshift? Well, these are a number of examples of Lyman alpha narrowband emission from KCWI, Subaru, Keck, Muse, and KCWI again. And these are on 100 or so kiloparsec scales, few hundred kiloparsec scales. These so-called giant Lyman alpha nebulae or Lyman alpha blobs are very ubiquitous at the high redshift universe, certainly above redshift of about 3. And there were a number of theory papers written, including by Avi, who's here in the audience, speculating at the time that this could be direct observational evidence of cold streams or cosmic web filaments. It was never really clear in these early series of papers what might power the emission, what is the actual source of the Lyman alpha emission. We're going to talk a lot about that for the rest of the talk. I do want to, though, also say that circumgalactic gas on hundreds of kiloparsec scales is not only seen in Lyman alpha narrowband emission, and I want to highlight this recent observational study that I was involved in using ALMA, where we detected a 100 kiloparsec stream. I didn't put the scale here, but this is about 100 kiloparsec stream observed in atomic carbon, which seems to be inflowing toward a massive radio galaxy at redshift 4. All this like purple is actually the Lyman alpha, and this is the C1. And the properties of this that we infer from this are actually consistent with predictions for the properties of cold streams that feed a halo of this mass at this redshift. I'll come back to that during the rest of the talk. And this actually shows that streams are not only 10 to the 4 Kelvin gas, as you might infer from the Lyman alpha, but they potentially host a lot of gases at temperatures as low as 100 Kelvin to excite the C1. And in addition, these streams are not pristine, as you might have expected intergalactic gas to not host any like metals, but they must have some like metals, because again, we can observe them in carbon. And that's actually not unexpected, because again, the low mass halos live within the large scale filaments, and they obviously have their own star formation, their own feedback. They're going to eject supernova ejecta into the cosmic web filaments that then go on to feed the massive galaxies. So we don't expect them to be fed by pristine gas, but by gas that is already enriched even at high redshift. On much larger scales, intergalactic filaments, not circumgalactic streams, but intergalactic filaments, this is also becoming accessible to us. This is an observation with Muse, and this is with KCWI. This is a very recent paper showing, again, narrowband Lyman alpha emission, not on scales of 100 kiloparsec, but on scales of 1 proper megaparsec in each of these images as well, showing what indeed seems to be the large-scale intergalactic cosmic web. Now, observations like these at the moment are very complex and very expensive, but when the GMT comes online, as well as Blue Muse in the next 5 years or so, observations like this down to redshift 2 are going to be much more accessible. And by correlating these types of observations with like mappings of the cosmic web based on the positions of galaxies using large-scale galaxy surveys like either Euclid or the Moon's survey, we could potentially identify where we expect intergalactic cosmic web filaments to be based on the galaxy distribution, and then go and target those regions using the GMT or Blue Muse, and thus get a real census of the gaseous properties of intergalactic filaments in different environments across cosmic time near that peak of cosmic noon, which could potentially be very interesting in understanding how galaxies of different masses of different environments are fed during that time. Okay, let's go back into theory land. Saying the galaxies are fed by cold streams is all well and good, but that is a slight wrinkle in that picture, where what happens above halo masses of 10 to the 12, Remember, we talked about that in the peak of the Mandelker plot, cosmic noon, typical halo masses are 10 to the 12. What's so special about that? Well, above a halo mass of 10 to the 12, the circumgalactic medium is expected to be hot. It's expected to host a roughly hydrostatic halo at the virial temperature, which is about 1,000,000 degrees Kelvin or more. Now, above redshift 2 during cosmic noon, the expectation is that these cosmic web filaments, because they're so dense, because they're so narrow, they're much denser than the ambient CGM. Their cooling times are a lot shorter than the cooling times in the ambient CGM. Therefore, they do not shock heat, but they're able to efficiently go through the hot CGM all the way down toward the central galactic disk, again supplying the disk directly with mass angular momentum, driving turbulence, driving disk instabilities, even if you're embedded within a hydrostatic hot halo. Now, cosmological simulations, almost all of them, seem to indicate that these cold streams that penetrate the hot halos, this is all well and good above redshift 2, but below redshift 2, this kind of goes away. But it's never really been made clear why it goes away, and let's spend a few minutes on that. So this is just to show you what I mean by cold accretion going away. This is by Van de Voort et al. 2011, Fauchel-Guichard 2011. This is showing the distribution of hot mode accretion versus cold mode accretion. So accretion from the hot phase versus accretion directly from cold gas from the intergalactic medium in halos of between 10 to the 12 to 10 to the 13. You can see that above a redshift of about 2, halos are dominated by cold mode accretion. Below redshift 2, you're dominated by hot mode accretion. Here you can see as a function of halo mass, so looking at 10 to the 12 solar mass halos at different redshifts, you're dominated by cold mode accretion. Above a redshift of about 2. Below redshift 2, cold mode accretion becomes negligible. You're dominated by hot mode accretion at those scales. That's in simulations. There's actually reason to believe that we're seeing this now in observations. This is a paper by Emanuela Dadi et al. 2022. You can see very similar results in Popesso et al. 2023. This is showing the star-forming main sequence of galaxies. This is at different redshift bins. So this is galactic star formation rate versus stellar mass. And it's roughly linear at low masses, but then there's kind of a turnoff mass where the relationship flattens. And if you mark the turnover mass and plot that turnover mass as a function of the redshift, let's call it the quenching mass, the mass where the star-forming main sequence flattens, you can see that below redshift about 1.5, it's roughly constant at 10 to the 12 solar masses where you expect the transition to hot halos. That's what you would expect. But as you go toward higher redshift into cosmic noon, this quenching mass goes way up by 1 or even 2 orders of magnitude in a way that so happens to really look similar to this magenta line, which is from Declan Birnbaum 2006, which was an initial crude attempt to estimate when would cold streams not be able to punch through the hot CGM surrounding halos because they themselves would also heat up. This is a very crude approximation, but it does surprisingly match the data well. This blue line, we're going to spend most of the talk deriving and discussing where this blue line comes from. This is my own model for, let's assume that the streams do enter the hot CGM. At what point do they get disrupted by hydrodynamic instabilities? And that's what this blue line represents, and this actually really nicely traces the evolution of the quenching mass into cosmic noon, which is at least suggestive of a link between the decline in cosmic web accretion and the decline of the quenching mass during cosmic noon. This can also be seen kind of indirectly by this plot from Baruzzi et al.'s universe machine showing halo mass versus redshift, and the color here is the fraction of halos at that mass that are star forming as opposed to quenched. And you can see that if you look at where are about half the halos quenched, that's again roughly constant below redshift 1.5 at 10 to the 12 solar masses, but increases toward higher redshift into cosmic noon in a way that approximately follows what you would expect for cold streams living in hot halos, just like the previous plot. So that leads me to my fundamental question, which I said was kind of maybe a little outside the box. Does a transition in the accretion mode from hot mode to cold mode accretion, the disappearance of cold streams, is that what directly drives a decline of the quenching mass during cosmic noon? And is the decline of the quenching mass during cosmic noon what maybe drives the peak of the cosmic star formation rate density, the Mandelker plot? Right? Because if at redshift 3 or 4, a 10 to the 13 solar mass halo is smack on the main sequence, if that were to continue down to redshift 0, that peak in the Mandelker plot would presumably move to lower redshifts, right, until the typical halo mass gets above 10 to the 13. So the decline of cold streams around cosmic noon might be directly influencing that peak in the Medal plot, and that's something worth exploring. What is it that drives a transition in the accretion mode? A few options come to mind. One, it could be a change in how dark matter halos themselves connect to the cosmic web. This is sometimes known as cosmic web detachment. It was proposed by Aragon Calvo in 2019, and we're currently exploring a more modern spin on this in my group. Something else that could happen is cosmic web filaments can no longer harbor cold streams. This is a paper of ours from 2024. I don't want to go into the details of it, but I will just say that just like halos, when they get above a certain mass, undergo a transition from having a predominantly cold CGM to a predominantly hot CGM. The same thing happens for filaments. When filaments get to be above a certain line mass, they move from being predominantly cold streams to predominantly hot filaments. And when this happens, that's completely unrelated to the CGM. This is an intergalactic phenomenon, and that could shut off cold accretion onto halos. Something else that could happen is that as the cold stream is trying to enter the virial shock of the halo, it's dense enough so that it doesn't itself feel a shock, but due to a discontinuity in the confining pressure around the cold stream, it can suddenly feel 20 times higher pressure, which causes it to undergo a radial shock, where it suddenly very rapidly will pinch in and then explode out and shatter into tiny fragments. This is something that we addressed also in a recent paper of ours from earlier this year. I'm not going to go into that now. What I will do for the rest of this talk, however long I have left, is are cold streams disrupted by hydrodynamic instabilities in the CGM itself? Okay, so let's now kind of introduce a toy model for the properties of cold streams as a function of halo mass and as a function of redshift. So there are three dimensionless numbers that define the simplest version of this problem. Number one is the Mach number, so that's the velocity of the streams with respect to the sound speed of the hot halo, which is at approximately the virial temperature. Since the velocity is about the virial velocity and the temperature is about the virial temperature, this Mach number is of order unity by construction. Second dimensionless number is the density contrast between the stream and the CGM. And if I assume that the hot CGM is at about the virial temperature, the cold stream is at about 10 to the 4 Kelvin, and they're in approximate pressure equilibrium, you can work out that, for example, a halo of 10 to the 12 solar masses at redshift 2 has a density contrast of about 200 between the stream and the halo. This is as a function of mvir on the x-axis in different bins of different redshifts. Now, if I know the density contrast, and I can somehow model the density of the hot CGM based on the density of the halo and some mass fraction of the hot component, you can model this. Combining these together, I can get at the actual density of the cold stream itself. So again, for a halo of this mass at this redshift, that's about 0.01 atoms per cubic centimeter. And once I know the density in the stream, and I assume that the stream is flowing in at the virial velocity, and I know the total accretion rate onto the halo, I can constrain that from cosmology, and I have a model for, okay, of the total accretion onto the halo, what fraction of the accretion is along a given stream, so then I know the flux along the stream itself. I can combine all these together to estimate the stream radius normalized by the halo virial radius, which is a third dimensionless number that defines the problem. And that turns out to actually not have any explicit redshift dependence. It only depends on the halo mass. And somewhat interestingly, we got out for free from this model that as you get below 10 to the 12 solar masses, this can approach 1, which is what you would expect because you're no longer at the node of the web. You expect to now be embedded in an individual filament, which actually makes a lot of sense. But this is about 10%. So, okay, putting all that together, the simplest thing you can do is, all right, let's derive the linear growth rate of Kelvin-Helmholtz instability in a system like this. So this is the number of e-foldings of growth due to Kelvin-Helmholtz instability as a function of the density contrast, the Mach number, and the size of the stream with respect to the virial radius. And this is where we expect streams to live. And the upshot here is that these numbers are almost always very large. So KHI is highly nonlinear. You might also notice, somewhat interestingly, that there's a phase transition in the instability mode here. This is actually an interesting hydrodynamic phenomenon where Kelvin-Helmholtz instability in subsonic flows versus supersonic flows is a qualitatively different phenomenon, which is super interesting, but I don't want to talk about it now because I don't have time, but those who are interested can talk to me later. That's just the linear growth rate. That's clearly not enough. Let's talk about nonlinear stream disruption. At what point do the streams totally mix in with the hot CGM? So So these are for the subsonic surface modes and the supersonic body modes. I don't want to go into the details, but you can analytically derive the timescales for stream disruption by these different modes. Unsurprisingly, it scales as the stream crossing time. Narrower streams are going to mix into the CGM a lot faster. That's not very surprising. And you can combine this together to make a plot like this. This is showing the largest stream in units of R stream over R vir that completely mixes in and disrupts into the CGM in less than a virial crossing time. As a function of the density contrast and the Mach number, again, this is where streams are expected to live. So, the qualitative number to keep in mind is that streams that are narrower than about 5% of the virial radius, which is certainly plausible, are expected to completely be disrupted and completely mix in with the CGM in less than a virial crossing time, shutting off cold accretion onto the galaxy. Wonderful, we've solved the problem. Except for what? I never mentioned cooling. Now obviously cooling here is critical. These are cold cooling streams. When you consider cooling, there's a fourth dimensionless number that describes the problem that you have to consider, and that is the ratio of the shearing time. What I mean by the shearing time is this time scale that we discussed here for the nonlinear disruption and the mixing of the stream into the CGM. Compare that time scale, which is itself linear with the radius of the stream, to the cooling time. Cooling time where? In the stream? No, not in the stream. In the turbulent mixing layer that forms in between the stream and the hot CGM due to the onset of Kelvin-Helmholtz instabilities, right? Where you have intermediate density and intermediate temperature gas. And you can relate this ratio of like time scales to R stream divided by R stream crit, which, never mind, but you can write out an expression for R stream crit. And for streams that are larger than this critical radius, you expect the cooling time to be short compared to the shearing time, and therefore cooling to be important in the overall evolution. This is a ratio of R stream over R stream crit, and as you can see, for the vast majority of the parameter space, this number is very large, implying that cooling will be very important. Now, remember this blue line? So this blue line is what you get for assuming that R stream over R stream crit is not 1, but is 20. Now, okay, wait, why 20? That's rather arbitrary. Well, I mean, it's a little arbitrary, but it's not totally arbitrary. I actually have good reasons to expect that you don't expect the critical value for this ratio to be of order 1. You actually expect it to be of order at least 10, and 20 is quite plausible. That's a bit of a technical discussion that I don't want to get into, but while I agree this value 20 is somewhat arbitrary, it's not totally made up. And the fact that it fits the data so well is well, cool, if nothing else. Pardon the pun. Okay, so what is evolution of KHI with cooling in this fast cooling regime? What does that look like? So these are simulations run in a periodic like box. These are runs where the cooling time is long compared to the shearing time. This is the same exact initial conditions, but rescaled such that the cooling time is short compared to the shearing time. You can see a qualitative difference in how streams evolve. In this case, you can see that the stream expands out into the background due to Kelvin-Helmholtz instability. The central density becomes very diluted because you're continuously throwing stream material out into the CGM and having it mix at large distances. Here, the densities in the center remain quite large, and the stream remains much more confined. And why is that? It's because as you try to throw stream material out into the CGM, it mixes with the ambient gas. The cooling time in that mixed gas is very short, so it loses pressure support and falls back onto the stream. It cools and condenses or entrains onto the flowing stream. That entrainment brings more and more mass onto the inflowing stream. It has to therefore share its momentum with more and more mass, and therefore the stream winds up decelerating. I should note, I would be remiss if I didn't note that very similar physics has been explored by a large number of groups over the recent years in the context of cloud crushing, which is kind of the opposite problem. I'm thinking of streams flowing in. They're thinking of clouds flowing out, but it's the same idea. What happens when you have a cold blob of gas flowing through a hot ambient medium in slow cooling versus fast cooling regimes? And it's very, very, very similar physics, just different geometries, which actually does lead to some interesting differences, but I won't go into that. So, okay, these are those same simulations that we looked at before, looking at the cold mass as a function of time. These are all runs where the cooling time is short compared to the shearing time. These are runs where the cooling time is long compared to the shearing time. And indeed, you can see that the cold gas mass grows in the regime where you expect it to, and it decreases in the regime where you expect it to. You can actually look at the growth rate, so the m dot of this curve, and that's what's plotted here, normalized in a way such that the dashed line is the analytical expectation for the asymptotic entrainment rate of hot gas onto the stream as a result of this KHI-induced mixing. And all of our simulations asymptotically reach this expectation to within a factor of less than 2, which is good. That's what you expect. So we know how to model mass entrainment onto the stream. Once you know how to model mass entrainment, as I said, that causes streams to decelerate due to momentum conservation. So this is the velocity of the stream as a function of time for all the different simulations. If I renormalize my time to not the sound crossing time, but the entrainment time scale, then this is the analytical prediction for how the deceleration should work. And you can see that all the simulations match this to a reasonable degree. That deceleration causes dissipation of kinetic energy from the stream. It also causes dissipation of thermal energy from the hot CGM as it's cooling through the mixing layer. And each of these processes can be modeled analytically, and the simulations match them quite well. So what I'm showing in this plot is our modeling for the dissipation of kinetic energy, the dissipation of thermal energy, with additional corrections due to a slight heating of the stream and generation of turbulence that I don't want to go into, but those are also factored in here. And these are all the simulations. This is just looking at cooling rates from the simulation. So you take the density and the temperature and the metallicity, and you look up at the cooling curve, at the cooling table. What is the net emission coming out of my simulation? And the fact that this can be modeled analytically, and this a really good match for each other, implies that we know how to model this analytically. And if you ask, okay, this is the total emission, what temperature range of the gas is doing most of the emitting? Well, most of it is coming out from a thin, narrow layer in the turbulent mixing layer right around the stream, where the gas temperature, so this is the temperature-weighted distribution of the emission, showing a sharp peak at temperatures just over 10 to the 4, implying that at least half the emission should indeed come out as Lyman alpha. So that ties us back to the Lyman alpha blobs, the Lyman alpha nebula that we were discussing. If I know how to model the emission based on my model for stream evolution, Kelvin-Helmholtz instability, turbulent mixing layers, etc., I know how to predict the Lyman alpha luminosity. Now, all of this so far has been based on, analytic theory, but really in simulations done in periodic boxes. What happens if I now take that stream and insert it into a dark matter halo potential? So if I take that stream and insert it into a dark matter halo potential, a few things are going to happen. These are simulations showing that. We now have a hydrostatic halo. So you have a background profile in the density and the pressure for the CGM and for the stream as well. You also have the stream becoming narrower as it flows in toward the halo center. You also have acceleration of the stream due to the gravitational potential of the dark matter halo. And we also here included both the UV background and self-shielding from the UV background when the gas became dense enough. So we took all of this, and we wanted to say, how do our predictions for Lyman alpha emission change or not change? And the kind of upshots of this study are in these two plots. This is looking at the mass flux of cold gas for different parameters of the stream, the velocity, the density, and the density contrast. The dashed lines are analytic models that are based on the models I just described, but now I account for all the effects that I said where the stream becomes narrower, the densities have the equilibrium densities have a profile. You can factor all that into the model and still predict m dot, and the solid lines are simulation results. So the simulation results match our analytic models to a really good degree. And these are models for the predicted Lyman alpha luminosity. Again, analytic versus measured in the simulations. And again, the simulations match the analytic theory superbly well. So all of our previous predictions still hold. Now, this was run for a given halo. This was run specifically for a 10 to the 12 solar mass halo at redshift 2. But since we know that the simulations match our models so well, and our model is, you can scale it out to whatever halo mass or whatever redshift you would like, that allows us to make this plot, which is the total amount of Lyman alpha emission outside of 0.1 R-Vir as a function of halo mass in different redshift bins based on this model. And you can see that for halo masses of 3 times 10 to the 12 solar masses between redshifts 2 to 4, you can easily get Lyman alpha luminosities of a few times 10 to the 42 to a few times 10 to the 43. In more massive halos, you can even reach 10 to the 44 ergs per second. This can explain most, not all, but most Lyman alpha blobs or giant Lyman alpha nebula as a result of stream CGM interaction through Kelvin-Helmholtz instabilities, turbulent radiative mixing layers, etc. The most luminous Lyman alpha nebula, you probably need AGN to explain them, but I'm not going into that right now. The other interesting conclusion from this paper was, if we go back here, notice that the cold mass accretion rate onto the central galaxy is about 2 to 3 times larger than it was at the halo. Why is that? That's completely due to entrainment of hot CGM gas onto the cold stream. So you send in a cold stream with a given flux. You think that's the same flux that's going to accrete onto your galaxy. But in fact, because it drags in so much hot CGM gas along the way, you throw onto the galaxy cold star-forming gas at a rate 2 to 3 times higher than you threw onto the halo. That's kind of similar to what people mean when they talk about gas recycling. Gas recycling is usually supernova ejecta from previous generations of star formation falling back onto the galaxy, enhancing the accretion rate above the cosmic value. This is having that same net effect, but nothing to do with feedback. This is enhancing it due to entrainment of hot CGM gas onto the cold streams. And when you fold that kind of entrainment into a bathtub model where you assume that star formation rate follows accretion to first order, this is specific star formation rate as a function of redshift. These are observations. And this black line here at the bottom is the simplest version of the bathtub model that you can do based on our 2014 paper, where you assume the star formation rate follows cosmic accretion. And as you can see, between redshifts of 2 to 4, you underpredict the specific star formation rate by a factor of a few. This was highlighted already in our 2014 paper. But if you account for the entrainment, and I don't want to go into the details, but we have a more sophisticated model where we model the entrainment rate as a function of redshift, accounting for the hot versus cold fractions in the streams and the halos. The point is that you very nicely can fit the data, and you even for free get the fact that the discrepancy at redshift 2 was a lot larger than the discrepancy at redshift 4, for example. And that comes out due to the expectations of entrainment. So this might be a very interesting avenue to explore for star formation. All right, how much time do I have? Perfect. Let's take a breather. Let's add a new piece of physics now. So we talked a lot about cooling. That was fun. Let's throw in magnetic fields into the mix. This is work in preparation. When you account for magnetic fields, there's a fifth dimensionless number that you have to now consider. That's what's known as the plasma beta parameter. Plasma beta parameter is just the ratio of thermal pressure to magnetic pressure. Now, these are examples of MHD simulations without cooling, run by Thomas Burlock and Christoph Frommer in 2019. This is a pure hydro run. This is a run with plasma beta of 10 and plasma beta of 1. So this is magnetic fields and thermal pressure are in equipartition. This is magnetic fields that are 10 times weaker or 10 times less pressure than the thermal pressure. What you can see is that already at a beta of 10, but certainly at a beta of 1, you really suppress the mixing of the cold stream and the hot halo. This is not surprising, right? This has been known since Chandrasekhar, that magnetic fields suppress mixing and Kelvin-Helmholtz instabilities. That in and of itself is not surprising, but the quantification of this, so this is now looking at the dense mass as a function of time for the hydro run, the MHD with a beta of 10 and the MHD with a beta of 1. And they basically found that for strong magnetic fields, they could extend the lifetimes of streams by at least a factor of 8, just due to the suppression of the mixing by the magnetic fields. Again, without cooling. Now, the question is, what is a realistic value of plasma beta to assume for these cold streams as they flow into RVR? Obviously, the magnetic fields on circumgalactic and intergalactic scales during cosmic noon are not very well constrained. But we can look at a few different simulations to try and get like a ballpark number. And first paper I saw to kind of really do this in sufficient detail was by Rüdiger Pachmor et al. 2019. This was for a Milky Way. This is basically for a Milky Way halo. I think it was the Auriga suite of simulations, finding that at redshift 2 to 3, they obtained plasma betas of order 100 to 1,000 near the virial radius. This was our paper from a year ago showing that for more massive halos at higher, like redshift, you would get plasma beta values that actually approach 10 to the 5. And similar numbers were quoted by this paper by Ledos et al. From last year as well. So, pretty large plasma beta values, certainly larger than we see here. You might ask, is this already enough to converge back to the hydro result? Are plasma beta values of this, are magnetic fields this weak going to have any effect on the evolution whatsoever? And also, these are run without cooling, and they suppress the mixing. The whole effect of the cooling that we've been talking about, for example, the Lyman alpha emission, which was a really nice result, and the enhancement of the specific star formation rate, which is a really nice result, that all relied on entrainment, which relies on mixing. So if magnetic fields are suppressing the mixing, are all those previous results now made invalid when I put the magnetic fields in? So that's worth exploring. Yeah?
Could you clarify, because neutrals are not supposed to couple to magnetic fields, so what is the neutral fraction in this? Because it's not necessarily a plasma, right?
Fair point. Once you get down toward the center of the galaxy, it's probably questionable what the neutral fraction is because they're certainly highly self-shielded. But out near RVR, they're still predominantly going to be ionized. Yeah, the stream itself near RVR is still going to be mostly ionized. It'll be like partially self-shielded, but you'll still have like a neutral fraction of maybe 10% or so. Yeah.
Comment on that. Ionization fractions of 10 to the minus 5 or 10 to the minus 6 are sufficient in the interstellar medium to largely ensure ideal MHD. So I see no problem in these environments.
Even better. Okay, then thank you. You certainly have ionization fractions well in excess of that. So yeah. Okay. So now, as I said, this is work in preparation. I'm currently writing this up. I mean, like the work is done, but the paper's in preparation. So these are now simulations with MHD and cooling. These are runs with Mach 1 and density contrast of 100. These are Mach 2 and density contrast of 50. This is showing the cold gas mass over time, and m dot, so the numerical derivative of these curves. Again, I have here a pure hydro run. I run with a plasma beta of 10 to the 5, 10 to the 4, 1,110. Run with cooling versus without cooling. Okay, so you have a lot of information here, and the same thing here. Immediately you can see that in the runs with cooling, the growth of the cold mass declines as my magnetic field strength increases. In the runs without cooling, the decline of my cold mass declines as I enhance the magnetic field. Unsurprisingly, it's just suppression of the mixing. The effect is more pronounced at Mach 1 than it is at Mach 2, but it exists in both cases. If you look at m dot, from the hydro run to the initial beta 10, you drop your m dot by a factor of 30. So it's quite large. So can we incorporate this into our models and derive everything self-consistently? Is this mostly due to magnetic pressure suppressing condensation or to magnetic tension suppressing the turbulence and the mixing? And how does the MHD converge to the hydro with versus without cooling? So let's look at some pretty pictures. These are slices of gas like density and the plasma beta parameter for a hydro run, an initial beta of 10, 1,000, and 10 to the 5. If you look at the initial run with the initial beta 10 run, you can see that the density is really laminar, certainly compared to the hydro run. Inside the stream, you haven't really done anything near plasma beta, but at the boundary between the stream and the CGM, you've enhanced your magnetic fields pretty dramatically to the point where locally beta is 1 or even below 1. And that's mostly due to compression of hot CGM gas that cools in that mixing layer, as it were, and enhances the magnetic fields. As I lower my initial magnetic field strength, I get more mixing. In the case of beta equals 1,000, I can still find a lot of local patches where the beta is less than 1. When I start with a beta of 10 to the 5, I rarely have any patches where locally beta is less than 1. Beta is almost always above 1 here, but it's still enhanced by a large factor. But the fact that you never reach beta of 1 is why this, morphologically looks very similar to this, whereas this is kind of intermediate between 10 to the 5 and 10. A bit more quantitatively, we can ignore the plot on the right. Let's just look at the plot on the left. This is showing a radial profile of plasma beta for a run with an initial beta of 10, 100, 1,000, 10 to the 4, 10 to the 5. So again, for the beta of 10 run, you see a sharp enhancement of the magnetic field strength only at the boundary between the stream and the CGM. But inside the interior of the stream, you haven't really done much to the magnetic fields. But for all the other cases, you've enhanced the magnetic field inside the stream itself. And note that even for the initial plasma beta of 10 to the 5, you can almost reach equipartition inside the stream. This is on average a beta of 10, but you have regions where you're in a slightly lower value of the beta. This actually implies a magnetic field strength in the stream. If we assume that the streams start out with a beta of 10 to the 5, that means that in the stream itself, by the time you reach the galaxy, which is about what this profile is meant to represent, you can have magnetic fields of order 0.1 to 1 microgauss in the cold gas in the stream. That's potentially a really interesting way to transport magnetic fields into the galaxy via accretion, by enhancing the magnetic fields in the stream due to turbulent mixing. Let's look at phase diagrams of the gas. So this is entropy and thermal pressure in a hydro run with no cooling. So what happens here is that at roughly constant pressure, I mix in my cold gas into my hot CGM, so low entropy gas turns into high entropy gas. This is a hydro run with cooling, so here the opposite effect happens. My high entropy gas cools and becomes low entropy gas, but because of the cooling and the subsequent large turbulence that is generated, I have a pretty large spread in thermal pressure. Okay, what happens with cooling but a plasma beta of 10, again showing entropy versus thermal pressure? Well, you have a similar spread in thermal pressure, but as opposed to here where you could at least still see the ridge line, which was at roughly constant pressure, here you don't even have the ridge line anymore. There's no reason to assume that anything is happening in constant thermal pressure here. But what about magnetic pressure? If you change your x-axis to be thermal plus magnetic pressure, everything is very, very isobaric. So I want to take us back to this plot of the entrainment rates. And how can we fold magnetic fields back into our model for entrainment and everything that implied? You'll notice that in my normalization for m dot here, there's one factor that depends on the cooling time. Cooling time depends on the temperature and the density. So what temperature do we mean here when we talk about the cooling time? Well, we usually mean the temperature where the cooling time is at its minimum, which is usually at like 2 or 3 times the equilibrium temperature of the cold stream. So whatever, 3 or 4 times 10 to the 4. But to compute a cooling time, I don't just need a temperature, I also need a density. What density am I inserting into my cooling time? Well, what was assumed here was I know my temperature, so I'm going to take my density given thermal pressure thermal pressure equilibrium. That worked well for the hydro case, but obviously not for the MHD case, as we just showed. But if I now change the density that I insert here into the cooling time to account for constant thermal plus magnetic pressure and keep everything else the same, now all of my curves except the beta equals 10, which is admittedly, this is not sufficient, but for beta equals 100 and above, all my curves have now collapsed. This is sufficient to now model entrainment with magnetic fields by just changing the density that I use in my cooling time. So if I take that realization, I can now go back to computing my Lyman alpha emission rates. And long story short, the green is the hydro run. This is a plasma beta of 10 to the 4, 10 to the 5, and 1,000. I would argue that for a plasma beta of 1,000 or above, which I think is very realistic for the circumgalactic medium, I don't lower my Lyman alpha emissions by maybe by a factor of 2. So all my nice predictions for matching Lyman alpha blobs, etc., are not changed by MHD, nor are my conclusions regarding enhancement of specific star formation rate due to entrainment. Now, I don't have time. I'm going to skip to the summary, but for those who want to talk to me later, we've also folded self-gravity into this, so that's dimensionless number 6. In the interest of time, I'm going to skip over this just to leave you with something that you might want to talk to me about. Self-gravity can be important in streams. These streams can be gravitationally unstable. And we had a paper a few years ago showing that at redshift greater than 5, the gravitational instability in these streams could be sufficiently high so as to have them fragment and form stars, potentially even globular clusters in the circumgalactic medium around massive halos at that time. Jake Bennett had a simulation several years ago as well showing star formation along cosmic streams in agreement with our model from here. So star formation in these filaments due to gravitational instability, which would relate to the C1 observations of the 100 Kelvin gas talked about, right? That's a potentially really interesting thing to follow up with JWST. But we don't have time for that, so let's just summarize. Massive galaxies at high redshift are fed by cold streams from the cosmic web. These supply both galaxy disks and the CGM with mass to fuel star formation, angular momentum to grow the disk, and energy to drive turbulence and to drive disk instabilities. The details obviously depend sensitively on the thermal, kinematic, and morphological properties of the stream as they reach the disk, which is one of the motivations for this entire study. There's an increase in the quenching mass at redshift 2, which seems like it might be directly tied to the evolution of cold streams. At redshift smaller than 2, streams begin to move from the fast to the slow cooling regimes and are disrupted in the CGM by KHI. But at higher redshifts in cosmic noon, the streams entrain mass from the CGM through turbulent radiative mixing layer. Cold gas accretion rates can be about 3 times larger than cosmological, which might help explain specific star formation rate observations at redshifts 2 to 4. And the dissipation is directly tied to Lyman alpha emission in Lyman alpha blobs. MHD enhances stream survival further. Fortunately, the entrainment and the emission are similar to the hydro case, so long as my initial plasma beta is 1,000 or more, which I think is very reasonable. But as I mentioned, magnetic fields in the streams can be amplified to almost equipartition, and this could be a really interesting way of growing galactic magnetic fields. Self-gravity, which we didn't really discuss, but it's just to say that it can lead to star and globular cluster formation in the CGM at redshift 5. And of course, there are additional issues affecting cold gas accretion, cold versus hot gas fractions in cosmic web filaments, and the potential shattering of streams at the virial shock due to pressure discontinuities, which I'm happy to discuss further while I'm here. So thank you.
Thank you very much, Nir. I've got some time for some questions.
So clearly the streams start from very large scales where they are much wider than the virial radius of the galaxy, right? They start on a scale, I mean, we can see it in the simulations. The virial radius is a tiny region embedded within the intersection of... So my question is, we know that there is outflows, that there are outflows in these galaxies, and why wouldn't it prevent altogether the collimation of this? Because you're showing collimated streams on scales much smaller than the virial radius. So why do we get these collimated streams without any disruption?
So I would say that your original statement about the streams being much wider than the virial radius, it kind of depends what you mean. Certainly if you're talking about these halos, I completely agree. The streams are much larger than the virial radius of your typical halos, but these are not really the ones I was discussing. I was really talking more about the nodes. Now, even for the nodes, I agree with you that the size of the dark matter filament is probably comparable. I would still say it's a bit smaller, but it's not that much smaller than the size of the virial radius of the nodes. However, the cold gas component is really a dense, small isothermal core within the dark matter filament. So in the picture that I kind of showed quickly, but I didn't really discuss about the cold versus hot here. So when I talk about the structure of intergalactic filaments, this would be the scale of the dark matter filament. It's filled with hot gas at the virial temperature of the filament. But this gas proceeds to, cool through a multiphase, highly vorticical region, settling in at the center, which can be only 10% or so of the size of the filament itself. This is the cold stream. So this is actually a lot narrower than the size of the stream and of our Vir.
Nir, this is beautiful work. Thanks for sharing it with us.
Sure.
But
Thank you.
I do have concerns, in particular with respect to the numerical resolution, right? I mean, in principle, if you get the cooling physics right, you would, from a physical point of view, have to resolve the field length, which is completely out of range. So you do something that is somehow approximate, but, certain aspects of the cooling you just miss. And the same applies and is even more severe if you include magnetic fields. And so you talk about amplification, and I was wondering what exactly you mean. Do you really capture the small-scale turbulent dynamo that must be there and will lead to true amplification? Or when you talk about amplification, is it really just the compression of field lines as you compress the gas? Because these are two fundamentally different aspects. And if you miss the small-scale turbulence, you're missing lots of turbulence, you're missing lots of stuff that can lead to enhanced mixing. And so question is, what are typical resolutions you reach? Do you see really dynamo amplification? And what does it do to your magnetic field strength?
Thanks. So I think that most of the effect, the first order effect is really, in our case, mostly compression of the field lines as the hot gas cools onto the cold stream due to some initial mixing. That's certainly what happens in the run with plasma beta of 10. In the higher beta runs, where the initial field was weaker, we do generate more turbulence. We did look at the turbulence here. I might have those plots in backup slides. We did look at the turbulence, and it's kind of what you would expect as a function of the plasma beta, given MHD suppressing the turbulence. So I do think that what's going on in these runs inside the stream is mostly a turbulent dynamo effect. You're correct that my inertial range is somewhat limited. So these simulations were run with 128 cells across the diameter of the initial stream. So, I mean, that's not bad. It's certainly better than you get in the cosmological simulation, but it is still much less than you get in a true, turbulent box simulation. So my inertial range is somewhat limited. I'm probably missing a lot of the small-scale dynamos, certainly in the initial phase of the narrow mixing layer. But I do believe that I am seeing turbulent dynamo effects inside the stream. I don't think I have those results here, but I have been trying to compare some evolutionary plots and power spectrum plots of the magnetic fields to predictions from one of Christoph Prommer's old papers about the effect of the turbulent dynamo. They seem consistent with expectations, but that book is still open on that one.
I mean, as a rule of the thumb, Christoph Federat, before Christoph Prommer,
Right.
has shown that you need something like 32 cells across, at least to resolve an eddy and then to find the small-scale dynamo. So I think at best what you have is marginal in that respect.
Yeah.
So there could be a concern. I was wondering, can you just double it or quadruple it?
In principle, sure, but that would be, I mean, perhaps for one flagship simulation, I could devote sufficient computing time to it. The MHD runs at our fiducial resolution, I mean, depending on the magnetic field strength, but they already took on Stampede 2, they took like 2 weeks to run.
Okay.
So if I were to double the resolution, that would become long. But yeah, it's worth doing. I agree.
Maybe one last question. I mean, now concerning the other Christoph, the Prommer,
Yeah.
who will probably have tried to brainwash you in terms of cosmic rays.
Yeah.
So can you include at least some of that physics, which will change yet again the dynamics in these systems?
That's on the to-do list. We haven't done that yet, but that's on the to-do list. To include both the effects of cosmic ray pressure in the streams themselves, and also something that I'm curious about is what do these streams, how would they impact, if at all, cosmic ray transport through the CGM? Could cosmic rays preferentially be transported along the filaments, especially if they have large magnetic fields? The answer, I mean, certainly if the magnetic fields are as turbulent as they are here, I mean, probably not. But if they're more laminar as they are here, then that might be important. So that's also something we're thinking about.
I'm afraid we need to vacate so they can rearrange the room for the next talks. But Nir is here for the rest of today and tomorrow, and please sign up to chat to him if you have more questions. And let's thank Nir again.